Hi, everybody. Thank you for joining us today. It's great to see the momentum this technique is gaining, and hopefully this webinar will offer insight on what is possible to achieve with phase coherence imaging. So a little bit of housekeeping prior to get started today. You'll see here on this webinar that you have a question box on your screen. And so we are live today, so please ask questions in there and we'll get to them at the end of this presentation. All right, so we'll also have a few questions for you as we progress with this presentation. So we appreciate your participation and engagement with us as well. So as you might have noticed, we are two presenters today. And so I'll start with introducing Trevor Tartaglia, and who's been working quite heavily with PCI lately. And so a few things I know about Trevor is that he has a background in engineering, that he spent 4 years in the Canadian Armed Forces prior to go and study engineering physics at Laval University with a specialty in material science. And in February 2020, Trevor joined our R&D department at Olympus, which is now, as you know, called Evident. And after 2 years with us, Trevor switched over to the product applications team, and he now has a role as a product application leader on the OmniScan team. I also know that Trevor is a bike fanatic, a fitness enthusiast, and that he likes to share his passion and knowledge with others. Since working with Trevor, I can say that he's also a problem solver, which makes him a very dedicated person to find the solutions to new challenging applications. And so as I mentioned earlier, Trevor has worked quite a bit with phase coherence imaging on many samples that we received. So he has many different damage mechanisms that he tested in the past year, really. And so that makes him a great resource on this subject today. As far as for myself, my name is Émilie Péloquin. I've been in the welding and non-destructive examination field since around 2009. So that's about 13 years in the field. I've studied NDT in college, so for all the main NDT methods in accordance to SNT TC1A. So that's your VT, your MT, PT, ET, all the T's. But my heart truly landed on UT. And on phased array UT. So since 2014 or so, I started using FMC and TFM more extensively. And so I've been involved in many codes and standards and organizations like API, ASME, as well as ASNT. So basically, if it talks about NDT, I like to remain closely involved. I tried at least. I also am the host of an NDT podcast called Inspect Tech that you can easily find if you're interested by searching on iTunes or Spotify if you're interested in finding more about it. So that's a bit about us, but for today, let's look at our agenda for the phase coherence imaging webinar. So the first thing we'll start in doing is looking what is PCI. Then we'll look at some of the advantages for using this technique. We'll look at what probe or which probe or group to use when using this technique. We'll also see some specific use case examples and some data that we'll look at together. And lastly, on how effectively we can characterize defects with PCI. But before we get started, as I mentioned, we have a few questions for you. So the first one, before we go too far, is that we want to know, have you used FMC or TFM before? So you can click on any of those. We want to know, is that something that you've been using, or that's something that you're just curious about? It helps us know how much we go in great details into the TFM part of this presentation, or if this is something you're fairly familiar with already. All right. So right now we're still collecting the responses. Thank you very much for those who are responding. And all right. Can you see it now on my screen, Trevor? First time I use this, so.
I see the results, but I can't tell if you're sharing the results or not.
Well, let me see.
So far, we've had 90% of people that have responded, so we can probably share the results.
Yeah, I'm trying to.
Okay.
Okay, I need to close the poll here. Sorry. Okay, there we go. And so now I can share the result. Getting the hang of it. All right. So yes, for 50% of you, which is a good number, 27% of you said no, and 23% said no, but I am familiar with the technique. All right. So we might not spend a great amount of time looking at the FMC and TFM portion of this presentation. We have a lot of material online, so we do invite you to go and look on our website for more about FMC and TFM. Thank you very much for that. All right, Trevor, all yours.
So thanks, Emily. So moving forward, we're going to just go over quickly what phase coherence imaging is exactly. Since it's in the NDT field, this is a fairly new technique. So as far as what the phase coherence imaging is, the process for acquiring data is going to be identical to FMC TFM, where we have our probe and basically fire the elements in sequence, and we receive on all the other elements. And by doing that, we're going to acquire n squared for the number of elements, A scans, something that resembles this. And using this is how we will generate our standard TFM image by summing the amplitudes based off of the delays. But the main difference where phase coherence imaging is going to be different is that rather than using the entire signal itself, we're going to isolate the phase portion of our signal. So each signal, each A scan is going to be made up of an amplitude portion and a phase portion. More or less, put simply, if we take this times this, is going to end up looking like this again. But for phase coherence imaging, all we're looking at is the actual frequency information of our signal. The big advantage of this is that it's going to be a normalized or nearly normalized signal. And really, the amplitude is not going to be taken into account once we look at the final image. How we can generate an image based off of that is what we find is that where we have basically background noise in our signal, so all these parts here that are very high frequency, that's what we're going to call the low coherence and high frequency variant noise, versus where we have a very coherent and uniform signal, which is a bit lower frequency. That's what we're going to call our high coherent signal. This means that PCI is going to be less affected by the attenuation, since the frequency information can still be acquired completely independently of amplitude, which makes the PCI technique have a better performance when we're using noisy materials. It also means that some of the smaller defects, like diffraction from crack tips and very small reflectors, are going to be a lot easier to see, because they're not going to be lost in any high amplitude signal that might be close to or around their signal, which is going to be very coherent. So by looking at coherence, how can we actually generate a signal? Using the same image, if we consider how our TFM image is generated, the same idea where we have our matrix, and I'm going to start talking with my hands now. It's a bad habit, I know, but I'm not able to do without. So if we have our box for a TFM image, at every point in the box, rather than adding all the amplitudes together, basically we're going to take all of our n A scans, and we're going to look at that point in our box and we're going to do a statistical analysis between all of the A scans. And the closer the frequency distribution of our A scans is, the more likely we can say that there is a defect at that point. Because where there's a defect, all of the frequencies are going to be very similar and have a very small distribution. Whereas where we have just background noise, the distribution is going to be random and they're not going to be similar from one A scan to another. This means that we generate an image by comparing the coherence between the A scans, not just the A scans themselves, but by comparing one A scan to another, to another, to another. And because the maximum coherence value is 100%, this means that all the elementary A scans have the same frequency distribution at that point. And this means that, once again, that the PCI is completely independent of amplitude, because we're only looking at a comparison between the A scans rather than summing all of the amplitude values together. If you have any questions about the topic, because sometimes things can be a bit varied, there'll be space for that at the end. Like Emily said, you can add your questions into the chat and we'll try and address those after. But moving forward, Emily's going to talk to us about some of the advantages that this provides for inspections.
Thanks, Trevor. All right, so as Trevor mentioned, there's really no gain, or we're not looking at amplitude anymore. It's an amplitude-free signal. So what that means is also that is kind of impossible really to saturate the signal, which is a good thing, because when you are saturated, as you might know, with PAUT or conventional UT or TFM, conventional TFM, then sometimes you need to go and do a rescan because you were way above your window. So here we have no gain adjustment for this. This also means that from one data to another, or from one operator to the other, the data is very consistent, because we don't need to adjust the gain. That means also that there is no need for, again, a pre-adjusting of the gain. So a TCG or a sensitivity is not necessarily required here, because we're not talking about amplitude. We're just looking at the phase information. So so properly selecting the wave set that we need is important. We can do that with the AIM tool, but there's no other calibration really needed for this method in comparison to a TFM with amplitude. So that means that it's more consistent scanning in between inspection, in between inspectors as well. And because there are fewer parameters to be adjusted with this technique. So the acquisition and the analysis will be more consistent. There's fewer groups that are often needed for the same inspection. So for example, if we have something that with an amplitude-based technique, so with PAUT or TFM with TT, let's say that we have TT and we have a little bit of sound I'm sorry, a reflector high in the upper corner, let's say, of our zone of interest. Sound might not go there, so we would use another group, or 4T, for example. But because here we're not really looking at the sound response or the amplitude response, as long as there's sound going there, we'll see the diffraction, we'll see the change in the phase. So often we've noticed that we need fewer groups to perform the same coverage. Tip diffraction are much more obvious and can be used to size accurately as well. So we'll show some data and we'll show some example of that, but it is much easier to see a strong signal from those diffraction than relative to what we would used to see with reflection with amplitude. There's a better imaging to large reflectors, so especially back walls, and again we'll see some pictures of that, but with an amplitude-based technique, often the back wall is very loud, and if there's a reflector or some indications that are very close to the back wall, it can be hidden or the resolution might not be great. So this is another advantage of the PCI technique. And of course, sizing that is easier with fewer manipulations, and that we'll look at as well. Typically, it's very easy to see where the cursors will go, and it makes for a very fast analysis. Next slide. Now for the group and the probe and group selection, Trevor. Oh, I think you muted here.
Classic. After 3 years, we still haven't gotten used to it. So moving forward, I'm just going to discuss some of the probe and group selection rules or kind of best practices that we want to use using PCI, because there's a few changes from our standard amplitude-based techniques that we want to apply in order to have the best results as soon as possible. But in general, some quick tips is we want to use a higher frequency probe with more elements to yield the best results. And in general, we want to double the probe frequency from our standard inspection. So if we normally use a 5 megahertz probe, we want to move into something that's a 10 or a 7.5 and vice versa. But also the acoustic influence map or AIM that we have on board the OmniScan is still a very useful tool when selecting groups, because the sound distribution of the part must be adequate in order for the technique to be effective. So discussing the AIM, like Emily was mentioning, we're less sensitive to the distribution in the part because we're able to pick up on much lower amplitude techniques, but we still need to have sound that comes into each area of interest. So here I have a TT group with an angle beam. This is from an A32. So anywhere where I do have a color distribution right up into here is still going to be valid using PCI. With TFM, when we're getting these low amplitude areas, it might be a bit more difficult to see the image, or you might have inconsistent imaging from the whole, say at this bottom corner versus this bottom corner, because the amplitude is much lower. But with PCI, we're going to get a good distribution throughout the entire part. Up in the top corner here is probably not as valid, just because logically with a TT group, we'd have almost no sound getting to that point. With our 4T group, same idea, but here with 4T, we can pretty much cover the entire part. Maybe in the top corner here, a little bit better, not quite as good, but that's to be expected. But in general, when using PCI, the TT and 4T groups are going to be extremely effective, and we can usually cut out some of our groups. So say for this weld inspection, if we wanted to cover the entire part for all the different types of defects possible, I might actually need 4 groups, 2T, 3T, 4T, and 5T to get a good distribution. But actually using PCI, which is these two groups, we're going to have a better image than we would with 4 groups using conventional TFM. So as far as our probe selection goes, frequency, we want to move into a higher frequency probe. Like I said, generally doubling the frequency is a good starting point. The number of elements, using the maximum elements possible. The reason for this is with the statistical analysis that we're doing, the more data we have, the greater contrast there will be between background noise and coherent signal. The same idea that if I have only 8 signals, and 2 of them are the same, they're 25%. But if I have 64 signals and only 2 of them are the same, the actual percentage is only going to be 1/8 of that level of coherence. So the more sound we have, or the more A scans we have, the better resolution we're going to end up with as far as PFA sequencing machine goes. For sparse, obviously the best image quality comes with full matrix, just like with regular TFM. But when scan speed is the priority, we can use the sparse to improve productivity. Also with the same idea, we want to have as much sound going to the part as possible. We want to crank the voltage up to the highest level. So on the OmniScan X3 64, that's up to 160 volts peak to peak. And the element pitch, we want to use a larger element pitch for our probe. So we're gonna have some comparisons later that show an A32 versus an A31, and there is a difference between the slight change in element pitch between these two. So just a couple of slides to compare with images between the two. So the effects of a higher probe frequency. This here we're using an A32 with a 10L64 versus a 5L64, and the main difference is like the actual image is going to have a better resolution and less noise with the higher frequency probe. Here comparing the actual number of elements. So here with an A31, slightly different probe, with a 10L64 with versus a 5L32. Again, because we have 10 versus 5 megahertz for frequency, the actual resolution in the 10 megahertz image is better. But we can also see that it's harder to see the tip diffraction from our lack of fusion using the 32 element probe. There's even more noise. So this is going to be not quite as easy in order to size our actual defect. So here we have the tip diffractions, which are really obvious. With this one, we're going to have to look a bit closer to actually distinguish where our tip diffraction is. And then with a higher element pitch, same idea with the 10L64 and A32, which is a larger pitch than our A31. So even if it's the same frequency, same number of elements, the resolution is a bit better. And once again, seeing these tip diffractions on either side of my lack of fusion is not quite as easy. You have to spend a bit more time actually using the A-scan to find the tip diffractions, versus with higher frequency probe, they show up right away. The higher voltage, it's kind of counterintuitive because we're used to having more background noise in general when we increase the voltage. But here with a contact probe, it's pretty much the worst situation possible. This is with 10 volts peak to peak versus 160 volts peak to peak. And we can see that we have much less coherent noise throughout our entire scan, particularly close to the surface of our part. One thing that we have found is actually very effective for reducing that high frequency noise, or not high frequency noise, coherent noise, is actually the use of a filter. So in general, applying an 8 megahertz high pass filter, or whatever is just below the frequency of our probe, is very effective at cutting out a lot of that that coherent noise that we can see in certain images. And the same idea with the sparse setting, that when we are using the sparse setting, some of that coherent noise at the top of our part comes back, but this is still a very usable image, and we can still see quite a lot of detail in our actual defect. So the sparse, like I said, can very easily be used to increase productivity when it's necessary.
All right, thank you, Trevor. And there's some very good stuff in there. So the next question that we have for you, and I see that some of you have started to ask questions already in the question area, so thank you for that. The next question we have for you is, in which industry are you in? So you signed up today, we appreciate it. We want to know if this is also relevant for the applications that you would be using in the daily. So the industry that we've put here is aerospace, oil and gas, power generation, but there's also other if none of these apply. So we would appreciate your responses on this. All right, with 83% people voted, 87. $91. All right, 91. Think we can share the results. All right, 13% of you said aerospace, 49%, so the majority of you in oil and gas, 10% power generation, and 28% in other. If you can write the industry in the chat, I would appreciate it, so I can we can adjust also for other the next time. All right, thank you so much for that. Trevor, I'm not sure if I can, oh, there we go. Yeah. All right, so now some of the use case examples, some more concrete data that we can look at together, and also giving you some examples of what we tested thus far. Thank you. Okay, so for small defects, especially we've realized, so for HTHA, also creep damage, something that is very close to a specular small reflector, in comparison to a regular TFM, we've noticed, as we mentioned before, that the back wall and large specular reflectors are less visible, and then small cracks will stand out much more. So the back wall will be less loud, and then the smaller, very small defects or bubbles or intergranular cracks will appear very, very nicely. The reason for that is, again, the tip of the cracks diffract the energy, and that generates a very strong phase coherence in comparison to the large specular reflectors that are close to it. Also for attenuative material, and by this one we can talk about stainless steel, we'll talk about that in the next point, but also for very thick components. So that's a problem for UT or conventional UT, conventional phased array, conventional TFM. When we look at the amplitude, we often going to lose a lot of that sound in the part. So the defects are more uniform with PCI throughout the zone of the part, and they are still visible at a great depth because, again, we're not looking for an amplitude, we're looking for a diffraction. So the phase is not affected by that amplitude loss of the signal, and so even the signal amplitude that is weak in the coherence data is still valid and shows up very nicely. But as I mentioned, for noisy materials as well, PCI signals generated from noisy elementary A-scan is cleaner and the defect better image. So as Trevor mentioned earlier, actually we need that noise to have a very nice data. PCI does not perform very well on a extremely clean sample with a fake notch in it. We need those facets of the crack for the diffraction. We need that noise to compare what's coherent from what's not coherent. So again, noisy material is better for PCI. The data is improved by noisy material because there is a greater variation in the phase variance between the background noise and the signal from the defects. It improves sizing, as I mentioned a little bit earlier. The signal is not changed since it's independent from amplitude, so there's less user error in that sizing. When the phase information is not changed during analysis, and the same defects will diffract in the same way and are displayed as hot spots, we can really see, the diffraction from those cracks, for example, and we'll look at that in the tip diffraction sizing technique section. Some use case for PCI, so small specular defects such as HTHA, as we mentioned. HTHA so far has been showing great results with PCI. So we've shown to provide better results than conventional TFM, which was also heavily used for HTHA inspection, so better than PAUT as well, in a lot of common challenging cases, as well as typical difficult defects, especially as I mentioned, not machined. So a notch will work, but it's not optimized. You really want a true crack with facets. That's how you'll represent it the best. When testing PCI, so try on real weld samples. If it was in service, even better, because typically it's a bit more coarse. And we've seen also, particularly with stainless, if it is a simulated defects, it's not going to appear as well. High temperature hydrogen attack, HTHA, as we mentioned. Creep, that isn't listed there, but we've seen some very nice results with creep damage. Stress corrosion cracking, or SCC, and other samples with small natural defects is where we see this technique shine. Thank you. All right, so here on the right with the blue background, we see a 10L, we see the TFM conventional. We use the 10L64 A32 probe directly in contact. This is also HTHA, as we saw earlier as well. And on the left here, we have the PCI with the white background. And so as we can see, we can still detect a little bit here with the TFM. We see that something's happening, but the signal to noise ratio is definitely not as good as what we have here with the PCI, and where we see the cluster or the little cloud of indications that are starting to connect together on this particular one with the PCI. And we can also see that oops, sorry. If you can go back just quickly, I wanted to mention the back wall. So that's what we were saying earlier too, that a very loud back wall when it comes to amplitude, and less so with the PCI. So again, the resolution and being able to see a bit better, or image a bit better what's close to the back wall is very helpful here. All right, next one now. Thank you. So this one is an interesting one, because that's the sample that we had for quite a while now that we've been using for a lot of our tests in our lab. And that's a 12 millimeter stainless steel plate that had porosity in it. We knew it had porosity, but we thought there was one single pore. We tested it with UT, we tested it with PAUT, we tested it with conventional TFM, which this blue image comes from a conventional TFM image. We can see, that large pore, or that single pore there. But when we tested it with PCI, we noticed that our sample actually had much more than we knew. So a lot of very fine porosity, little clouds of porosity that started to appear, as well as that single pore that we could see before. So again, because it was that noisy, you can see, there's a lot of noise in the signal here. Because it was that noisy, PCI did very well to contrast what was actual indication and what was purely noise. All right, next one. And this one here, so to show again the small reflectors near large reflectors, being able to, again, because it's not amplitude, it's not as loud, the small reflectors can show much better. And so this effect is amplified when these defects are near flat reflectors, such as the back wall, since these flat reflectors are less apparent with PCI. And also defects with complex or non-linear geometry. So when the defects change direction or have a very complex geometry, it can be difficult to see the entirety of what's going on with one group. And so PCI helps there as well. If we're looking at ID crack or something that is connected, often we'll need more than one group to see if it is the same crack, or to what extent, how high it goes in the material. So PCI can help there as well. Instead of doing 2T and 3T, for example, here, probably one group would be sufficient. So these defects can be much more easily visualized, true to reality. And so another application that we found PCI to be very interesting is with ERW. This is a hook crack. So hook cracks are mainly manufacturing defects, really, but that they can, in service, start to grow even more. So it's kind of a cold lap. We still call them crack, but they're very large reflectors typically. Well, not true. They can be fairly large, but they can also be very small. In this case, it was a fairly large reflector, so we were able to see it with the conventional TFM. But to image the defect fully, we needed, as I mentioned earlier, those two groups. So we had 4T and 3T to be able to see if this was truly connected to the ID, and how far it was going into the material. Is it getting closer to my surface? And so here, with one group of PCI using 4T, we were able to see the full crack, the full hook crack. And the next one, please. And then lastly here, another ERW indication, which is a branch crack in this case. And we can see it very well on the TFM, conventional TFM with the blue background, very loud signal. But we know that this is a bit more true to geometry here with the branch crack, and sizing will also be easier to do with the PCI, having hot tips to place the cursors on. So this is another advantage here.
So another use case where we're finding really good results with PCI compared to amplitude-based techniques is with noisy, coarse-grained, or highly attenuated materials. Like we mentioned a couple of times before, this is where PCI is really going to shine compared to conventional TFM or amplitude-based techniques, because we're actually going to have a better signal-to-noise ratio because the contrast between the two is going to be much greater. So moving back to the same weld sample that we saw the porosity in, but using this time a lack of fusion. So lack of fusion, we knew it was there. We've always been able to see it. It's not particularly hard to see if you're using a group that's correctly oriented. But one big difference here with PCI is the appearance of the tips of our lack of fusion, which are causing a diffraction pattern. So we can kind of see them. If we increase the gain quite a bit, we can see them a bit really high. We can start to see them a bit more with regular TFM, but with PCI, we can see the reflection from the surface of our lack of fusion and then the two tips at either extremity. And that's making sizing of these kind of defects a lot easier because we can just place our cursors directly on the ends, which are highlighted by the technique, rather than having to do establishing my gain at a reference and doing a -6 dB drop in order to find the size of our lack of fusion. But as far as how sizing can be easier using PCI, we're going to talk about it a bit in depth a bit more a bit later. But another use case that's not in metals right now is with HDPE. This is something that we've just recently looked into a bit more, but we're having promising results in these kinds of materials in seeing having a better signal-to-noise ratio and seeing defects much more efficiently using PCI versus, say, TFM or phase array. The big defects in TFM are still visible. We can see a lot more detail here in these bit deeper parts, the deeper section of the part using PCI, and same thing with phase array, where we can still see the deeper portions of our part, but we're not getting nearly as much detail in the middle here as we are with PCI.
All right, now for our third question to you guys. We want to know from what you've seen thus far, do you think the PCI technique would be beneficial for any of your applications? So I know we're not going in great details in the answer. It could be yes, no, maybe. You can put more also in the chat. We're curious to know if there's something we haven't covered today, anything that that you think that this might work well on a specific damage mechanism or application we haven't covered. Please let us know. That would be much appreciated, and we can look more into this for our next webinar. So now we are about at 84% of you has answered. I'll give it a little bit of a bit more time for you to answer. And we should be close to that. All right. Okay, so am I sharing? I'm not sharing yet. There we go. By the end of this, I'll be good at this. All right, 69% of you said yes, 1% said no. Okay, and 30% said maybe. So okay, so for those maybes, would like to know again, which application you have in mind, and maybe we can discuss after the fact and see if that would apply or not for what you're trying to achieve. Thank you very much for that.
So moving forward into how we can actually use PCI to have a better characterization of defects, because that's going to be one of its main advantages that we've been mentioning since the beginning, is that it's easier and better to do sizing and characterization than with amplitude-based techniques. So the first bit is actually using the tip diffractions to do sizing. So one comparison we like to make is that using time of flight diffraction, so TOF, is often used for some of the same kind of defects in order to actually size them. And it's the same idea that we're looking for the change in phase in our A scan in the TOF, and that's how we're going to actually size the defect rather than using the amplitude of the signal. PCI is going to be very similar, where we can actually see an increase in the level of coherence at the tips of our defects, but we don't actually have to change the gain in order to do any of our sizing. One of the ways that we can validate this, so this isn't necessarily a calibration, but more a validation of a technique before we do an inspection, is we can use a notch in order to verify that the velocity and all the other parameters are correctly set in order to size the actual notch itself. So by using the TT and the 4T groups, we can see the tips of our notch coming off as a bright point, a hot spot, and we can basically just place our reference cursor directly on that point, and then using our readings, we know automatically what the size of our notch is, which is something you can do also with amplitude-based methods, but the actual tip diffraction is going to be much easier to see using PCI. And obviously this is a calibration block, is a very clean sample, so there's not a whole lot of noise that can cut out or hide the tip diffractions in TFM, but when we come to a real sample, it's going to be a lot harder to see. Another example, we're coming back to the same hook crack that Emily was talking about earlier. So in order to size this crack, all we have to do is place our reference cursor, or place our data cursor on the last hotspot in our defect, and then using the A-scan, we find the peak, very similar to what we do in TOFT, but now this is a rectified A-scan rather than being the absolute A-scan. And by placing a reference cursor on the tip of our defect, using the readings, we automatically know that from my reference cursor to my measurement cursor, which is placed at my depth, this crack is 4.5 millimeters high, which is super easy. When we remember our TFM image from earlier, the crack was separated in two portions. So sizing this defect using PCI is going to be significantly easier and significantly faster than with TFM. Again, coming to the lack of fusion that I had an image of earlier, same idea, but we basically have to do the hotspots for our tip diffraction on both ends. So we find the maximum in our A-scan here, the maximum in our A-scan here, reference cursor, in the measurement cursor, and the same thing using our readings. We know that it's 3.2 millimeters high, and the index direction is width is 2.5 millimeters as well. So, and the total length of our lack of fusion is going to be 4.1 millimeters. So if the actual operation in order to do this is going to be maybe 3-4 clicks, and we know already the exact size of our lack of fusion, versus if we were to do this in an amplitude-based technique, it would be significantly more than 3 or 4 clicks.
All right, thank you, Trevor. Yeah, and so something else about characterizing defects is that, obviously when we have 0 degree, we can do something that is parallel to the surface pretty easily, but what's vertical is very important too. So here we're showing some H2S blisters where what's important with those stepwise cracking, also known as stepwise cracking, and what's important with this type of damage mechanism is to know if something is connected, if there is stepwise cracking. So is this connected to the ID or to the next blister? If so, if we can see a connection for the asset owner, it's much more important to know because it can zip open pretty easily at this point. If the component, if it's not connected here and it's just a blister, it can remain in service for quite a long time. But if not, again, it can create quite of a important damage, and it can burst very quickly. So that's what I wanted to show here. I put a little throwback to PAUT, and that's what we're seeing here. This is still an advanced technique, right? We're still looking at phased array. It's used heavily. It is still a very valid technique, obviously, but look at the difference for that blister. We can see very loudly the amplitude here, and for what's parallel to the surface we have a very nice reflector, so we know there's a blister, but do we know for a fact that it is connected here? I would probably want to use another method or another angle, another scan basically to know what's going on there and to make sure that it's not connected to the ID. As far as here with the PCI on the left with the background here, the white grayish background, we can easily see the connection with stepwise cracking. So it's just to show a little bit of that comparison of, again, amplitude, phase array to phase with the PCI technique. So also identifying phase and composition changes in a material. I saw a question in the chat or in the question box earlier, so that might answer it for you for some of the coarser material. So in amplitude-based techniques like TFM and PAUT, inclusion or other metals or clouds of pores can attenuate the signal, the amplitude of the signal, and it makes it harder to pass that cloud or to see what's past it. So the change in phase is just not affected as much by this, not as much as amplitude. So for example, if there's a HTHA cluster close to a crack that is occurring in the weld, same HTHA often will, you know, lead into a crack. So if there is a cluster that is very close to it, sometimes with amplitude, it's going to diminish a lot, you know, it's going to lose a lot of amplitude. And so with the phase, we won't have as much as that problem. Of course, as Trevor mentioned, the sound still need to reach the part, you know, that area, but it becomes still less an issue in comparison to an amplitude-based technique. With PCI, the individual inclusion can be differentiated from coarse grain. So we kept mentioning that we can really see small defects. So sometimes people ask us, you know, will I see all the grain and will I know the difference? And so yes, it will help you see inclusions from what's grain structure. And the image quality of far side defects in austenitic materials is maintained as well. So sometimes penetrating through that thick or that coarse weld material can be challenging, but with an amplitude technique, but with PCI, we see a lot of benefits there. It's also possible to differentiate the weld geometry from the base material. So that's interesting. It's not, doesn't work for everything, but we've seen it pretty frequently that there's a transition from the base material to the filler material, and we can see that in the zone of a low currents noise, and so therefore it images the shape of the weld. So if the asset owner, after 40 years with having the component in service, they might not have the drawing for that weld anymore. So sometimes it can be helpful. Sometimes you can see if it was a double V or a single V, you have more information about that given weld. And this could also be identifying the transition from hardened to soft steel. So sometimes if it's heat treated, they can be also decarburization when it's in service for a while, or other changes in that grain structure. Sometimes the PCI will pick it up because it's very sensitive to those very small changes in the phase and the frequency. All right, we are now at the question and answer section of our presentation. Yeah. So let me see what we have, and we have quite a bit of questions actually. Yeah. That's great. That's really good. All right, so one that I've seen, yeah, in research areas, that definitely. All right, so some are comments. So let me see if I can find a true.
So one question here that that I'm seeing is coming up a couple times is there any filter used to get a nice signal or reduce the noise in this technique? Yeah. So we can use filters, the same filters that are available in the OmniScan X3 64 for conventional TFM are also available for PCI, and it does help reduce some of the low or some of the coherent noise that we might find. So the kind of basic rule that I mentioned before was using a low pass filter just below the frequency of our probe does help quite a bit. But as far as actually getting to the signal itself, there's no filter that is applied before. So the signal is treated in order to get to that phase information, but we don't actually apply any kind of filtering before that, which means any filter that we applied was the user that decided to apply that filter to improve the image.
Yeah. Very, very good question. I found another one here. Actually, there's two that might be, fairly similar. So I'll try to answer the two. So one of the question was, is the color palette that you are using showing the showing amount of coherence or amplitude? And that's such a good question, because that's going to take a while to be able to change our brain on this, because we've looked at those color palettes for so many years looking at amplitude. But you're right, it is the amount of coherence and not the amplitude anymore. So we need to change our brain on this a little bit, because we're looking at the coherence of that phase shift, and how frequently it comes back. So the more coherent, or the more it's going to hit that same spot every time, then the more it knows that it's coherent, and then the higher it's going to be on the color palette. And somebody else mentioned also, that there was let me see how it was stated. Is the color palette that you're using? Okay, no, that's the one. And then, that there was some misconception in the field. Like, I saw some comments as well on this in the past, like that it's just a different color palette, or again, no, it's really a different method of acquisition. So very different. Yes, the color palette can look different as well, but it's for the reason that we explained earlier, the fact that we're looking now at coherence and no longer at the amplitude of the signal. So we really need to change our brains a little bit when we look at that. Red doesn't mean that it has a high amplitude, it just means that it's highly coherent.
So if I can go a bit further into how the color palette was designed, because we did make a specific color palette for this technique. I just picked up this picture because you can see the color palette for TFM and the color palette for PCI at the same time. And what we can see with the TFM is that there's a change in color at 80% and 40%. And the reason for that is making it really easy to see the switch between red to green for that minus 6 dB drop that is used for sizing. I'm not even pointing at the right screen, sorry. So from 80% to 40%, we can use that drop in order to make it easier to see the change from minus 6 dBs for sizing. But with PCI, what we notice is that usually our background noise is from 10 to 15%, so we want to have that gray in the background. But actual interesting defects started to be around 30% coherent. So that's why we started to have that more punchy color around 30%. And we wanted to have it a color that's contrasting a bit higher so that it really stands out. So the effect that it makes is we have that red, which we're used to seeing, but slightly different so that we know to look there. But we also have the halo around it from the yellow and the blue that makes it a bit more obvious to see. But once we get above that 30% coherence level, we have that yellow that's going to stand out from the gray, and we want to start considering those defects as being important. So the color palette is made to improve the technique, but the technique is made to improve the technique. The technique is not just the color palette.
Great point. Yes, thank you for that. Another question I saw is the minimum configuration for PCI. So somebody said the X3 32-128. Unfortunately, no, it's on the 64-128. It is pretty demanding on the processor, and so it requires the bigger X3 64-128 as of today. And something else that I saw. Let me see. Oh yes, great question. Where can we find? Is there any published paper? We just released a white paper on this at the end. Oh, Trevor, can you go to the next slide, actually?
Yeah.
I think we have yes, we put a QR code there. There's a FAQ there for most of the common questions. So you can take a picture with your phone, but there's also the white paper that is that is here, and we also put some other user content. So University of Ultrasonic with Shane Walton has created a great video. I strongly invite you to go and look into it. So there's other people that have started to use it in different ways. So it can be, there's a lot of good resources, not just from us on this, but from other people as well. This PCI technique we can apply without the support of the PAUT technique. Yes, it can be used on its own. It's very similar to TOF inspection. You know, that sometimes people use TOF on their own, or they will use also phased array to complement the TOF. So either way, of course, depending on what you're looking at. If you're looking at a regular V-weld, very standard in carbon steel, maybe you don't go overboard. But if you're looking at HTHA, you might want to throw everything you have at it to make sure that you're not missing anything. So that can be that can be used with other technologies. I have another one. If you do, you also have one? You were about to say something.
Well, I was just going to mention there's quite a few people asking to have a copy of this PowerPoint. So obviously this webinar is going to be recorded. You'll be able to watch it over again. But with the QR code that Emily mentioned, there is a very similar PowerPoint that we based this one off of, which is the Getting Started Guide to PCI, which covers a lot of the same information of how to select probes, how the technique works. So that's going to be the best resource as far as getting a copy of this PowerPoint.
Very good point. Yeah. I saw somebody who commented on in the industry, and they put mining, and I think that's a great industry for this, because typically you have very thick material, very attenuative material as well, and so I think PCI could be very successful there. But if you have samples, please share, because that's always what we need to test the technique, obviously. A lot of people talked also about codes. That's always a tricky discussion, because sometimes technologies go faster than the codes, and it goes this way. We create the technology, and then we need to implement them in the codes. So as of right now, there's no code stating anything about PCI. It's too new for that. But as we start using it more, eventually, yes, it will be just like time of flight, just like PAUT, just like recently TFM. It will be installed in the codes and standards, and we're working as well on this. And the more we can test on materials, and the more we can learn and use it, of course, the faster this will go.
There's been a couple of questions as well about thin materials and how PCI will behave on very thin materials. And PCI is actually very good with thin materials. So the main reason for that is that the signal of the back wall is not nearly as strong as it is with the amplitude-based techniques. So even in thin materials, we're able to see quite a bit of detail because our back wall does not have as strong a signal. So we have a couple. The ERW weld that Emily showed a couple of slides from is 1/4 of an inch, which is not super thin, but reasonably thin. But we have a couple samples that are 3 millimeters, 2 millimeters that we're still able to see and size things like cracks and notches in. So it is a good application for PCI with thin materials.
Yeah, and somebody also mentioned weld overlay. So again, changing from one material to another can be very obvious. We can see the weld, but we should be able to penetrate and to look on the far side. So depending on the material, of course, if it's if sound can't go through, well, then it just can't go through. But in theory, yes, that could work very, very well on weld overlays.
A question here about can we display more than one type of wave like conventional TFM? And absolutely. So basically all the capabilities in the OmniScan X3 with TFM are available with PCI. Right for now, the PCI is standalone, so you can either be in PCI mode or conventional TFM mode. but that means if you create a setup with a 2T, a 4T, and a 3T group, you can have them all in PCI at the same time and display them with the same layout that you would with TFM for the equivalent setup. And the big advantage with PCI, as is onboard the instrument, the productivity with 3 groups is going to be similar, maybe 10% slower than conventional TFM as a live image directly on board the OmniScan.
All right, and I'll take one more question. And I'm amazed by by your questions, by the way. They're all really good and very relevant to this. So much appreciate your participation and the great questions that you've been asking. So one other question is, any application for composite material parts? And that's a great question. So we saw a little bit on HDPE what it was capable of. It was the very early tests. We are doing more tests on other composites like CFRPs and so on. So that's still something that we need to prove and to see, having cracked it. It can be challenging to find those samples. If you have samples, please reach out to us. But this is something that we're currently investigating. And we do believe that it could have some benefits there as well. All right. Okay. So if we haven't got to your questions, first of all, we're sorry, but thank you for asking all of them. And we will get back to you. So we are saving all those questions for once we've completed the webinar, and we'll get back to you via email to answer them if we haven't answered them here. So I want to thank you all for your participation and for joining today. There'll be another session later today. So if another question come to mind, feel free to sign up for that other session later. And thanks again for your attention for today's webinar. Hope to see you soon.
Thanks, everyone.